Yes, I would highly recommend you email him, or he has a cell phone, call him up.
D is an Excel file, is that correct? Yeah, you told us.
I'm sorry, what's Excel file?
D, is that an Excel file?
Oh, he hasn't sent that PC to D5? Okay. Huh? Did you reply yet? Okay, I'll remind him for sending you. If it gets delayed, we will push the submission deadline then. Oh, Kai is here? Okay. Okay, let's, what we were discussing so far is really how to improve the solar cell efficiency. To answer that question, we looked at it is what are the losses? If you can minimize or avoid those losses, then efficiency will go up. So we looked at it, there are two kinds of losses, optical losses and electrical losses. In the electrical losses, we talked about ohmic losses, resistive losses, and the recombination losses. So last lecture, we looked at it, various places, the resistance can add to overall resistance in the solar cell. So we talked about metal lines, the bus bar, metal semiconductor interface, emitter resistance, the bulk wafer resistance, back metal semiconductor interface. So we come up, that basically there are 3 or 4 different losses, only few we have to worry about it. So we have some idea about the electrical losses. Today's focus is looking at the optical losses. Okay. So the optical losses can arise from several reasons. One is the surface reflection. The surface of silicon can reflect 35 to 50% of the sunlight, depending on the wavelength. So that's a big reflection loss. The other loss is we are putting the metal contacts on the top, and they can give shadow to the sunlight. So you have 3 to 12% of the sunlight loss due to the metal gradient. So that's another loss. The third one is near the band gap, The semiconductor absorbs weakly. So wavelength around like 1,000 nanometer is not completely absorbed in 200 micron thick silicon wafer which solar cell people use. So you have a transmission of the infrared near the band edge, that light is lost. So we have these 3 losses, and what we're going to discuss is really how to calculate these losses, how to minimize or eliminate these losses. So that's what this, today's lecture is. Now Thursday, I believe we have a lab scheduled. So I will talk to TA to send you instructions for the lab, and those who can come, they're welcome to go to the lab. Those who are off-site and cannot come, they can watch the video of the lab and do the lab assignment. Okay.
Yeah, I'm off site.
Will there be a parking available? Yeah, I don't think we have any special arrangement for the class for parking. So I would suggest you have two options. There are street parking, which you can use. Other one near the Cavaliers, hotel. There is a parking garage. I believe is like $2 for a day or something, whole day, and that way the most cost effective. It's a few minutes walk, but that's the cheapest. Any other question? So I will ask Tia to send you out a note, and Thursday there will not be a lecture, but will be a lab. So first, your experience of really about solar cell fabrication. So reflection, we will discuss how to calculate the reflection. The other thing we learn is how do we reduce the reflection. And there are two ways to reduce the reflection. One is just like regular anti-reflection coating. So blue in this diagram is your silicon and the red is anti-reflection. And by putting anti-reflection, you can reduce the reflection. The question always comes is, how much do you reduce, Okay, and we'll discuss that. Other way to reduce the reflection is roughen the top surface of the silicon. So when the sunlight falls, it gets scattered and gets trapped by the roughness, and that also enhances absorption. Okay. So the reflection you have from different surfaces. One is the metal reflecting, but that's only 5% of the area, but that's still highly reflecting. Other one is the reflection from the front surface, but then we also could have a reflection from the back surface, because long wavelength of sunlight will be able to travel through the 200 micron thin wafer, and when they come on the back side, they could get reflected. The only thing is we normally put some kind of a metal contacts on the back, and that should help to reflect back and increase the path length twice, The reflection is really, you can measure that separately, and you can measure the quantum efficiency, and by knowing the reflection and the transmission, you can calculate true or internal quantum efficiency. The quantum efficiency is number of electrons collected was the number of photons incident. So that's the external quantum efficiency, but if you divide by 1 minus the reflection, then you get what we call internal quantum efficiency, because it does not depend on the reflection. Okay. So the best ideal curve for quantum efficiency you want is flat 100% or quantum efficiency of 1, and then at the band edge it goes to 0. And that's what you like ideally. But practically you get a curve like it's shown in the blue, and like I mentioned last lecture, the rise in the left-hand side or shorter wavelength, that comes due to surface recombination. So shorter wavelength get absorbed near the surface, they get affected more by the surface recombination, and that's what leads to this slow rising. the drop, rather than a sudden drop, the slow drop in the long wavelength, okay, that comes also due to the recombination of the back surface and also could be affected by the diffusion length, Okay. If your diffusion length is long enough, then it's mostly a recombination. And it goes to zero at the band edge. So you have a quantum efficiency curve shown in the solid graph, and then you have a plotted generation rate, the generation of electron for different wavelengths. So you can see the lambda 1 shorter wavelength get absorbed near the surface and accumulates quickly. Longer wavelength goes more deeper, and even longer wavelength go much deeper. And that's how it's reflected in your quantum efficiency curve. Okay. So next, the question is how do we calculate how much is the loss, and how do we minimize that loss? So one principle is the light is coming on this silicon, which is the bottom one. You put a transparent thin film on top of the silicon. Now what the transparent film does, it has a different refractive index than silicon and even air. So now you created different interfaces. One is between air and the film. There is a difference in index, so there will be reflection at that interface. The film is transparent, so light will go through it, but then when it hits the silicon and anti-reflection layer interface, there will be some reflection. When it comes back, the reflected light, some will be reflected, some will be transmitted, and you will have multiple bounces, and it will be decreasing. Okay. So now you have is one beam coming in, but you have multiple beams which are generated. So if you want to achieve anti-reflection layer or the property, what do you like to see these various reflections, the phase of that? In order to achieve no reflection, okay, what's the phase difference you like to have? Go ahead. 5. The phase difference you want 180 degrees because you want to cancel these two reflections. Okay. So the light is not escaping, If you add them, that will enhance the reflection. So you need a film which can produce a phase difference of pi between these multiple reflections. Okay. Now question comes is to achieve a phase difference of pi by using this anti-reflection layer, what index and thickness I need to choose? I need to choose my index and thickness because that's what controls your phase difference. Because light travels and comes back, that's extra path length. Okay. So we need to find now is what is the index and the thickness of the anti-reflection we should be using, which will give an anti-reflection condition. We have a silicon, let's say we call it have index of N2. Anti-reflection, let's say layer has index of N1 and thickness D1. and air has index n0 equals to 1, we call n0. Okay. Any question? Okay, so here is the physical concept. When there is no anti-reflection, the light will reflect and then some transmitted. By putting an anti-reflection layer, you have a front surface reflection wave and you have a back surface reflection wave. And you can see that in the right-hand side, they are in phase. The maximum of one wave lies on the top of the maximum of the other one. Okay. That will give constructive interference leading to high reflection. But on the left-hand side, the maximum of one wave matches with the minimum of the other one. And that's the phase difference of pi of 180 degrees, and if they interfere, no light will be reflected. So that's what we use here. Okay. Now, how thick this anti-reflection layer needs to be? Well, the phase difference is given, the thickness is really wavelength over 4n1. Where is that comes from? Because you are traveling in the film one time, and then you go back again, twice. That's what gives you phase difference. So if you do a lambda over 4.1, okay, quarter wave, that's a quarter of the wave. That's what it is. Lambda over 4n1 is a quarter wave, but then you go twice, so that will make a half wave, and that will be a 180 degree phase difference. So we found just from the physical discussion that film thickness needs to be quarter of the wavelength divided by the index, because if it is air, then it will be quarter lambda over 4, but we need to take into account the index because the light is traveling in that medium. Okay, so we found the condition for thickness has to be lambda over 4n1. So if you are given a material substrate and asked to design an anti-reflection layer, you should be able to calculate what thickness to use. Is that clear? Okay. Then the other question is, what is the N1? Because N1 determines what material I should be using for anti-reflection. So now next thing we will look at is the N1. What should be the condition N1? Okay. So using the light as electromagnetic wave, people have derived the light amount reflected from a given surface is given by the R1 squared. R1 is the amplitude of the first surface reflection. R2 squared plus 2R1 R2 cosine of 2 theta. 2 theta is the angle of incidence divided by this term where R1 and R2 are related to the index. Okay. And theta is the phase difference. And that's given by 2 pi n1 d1 over lambda. Okay. So this reflection, the expression has been derived using the electromagnetic, interaction with the material. Now we can use that and find the condition for the index. Okay. So one of the conditions we say is that the reflection is minimum when N1 D1 is lambda over 4. That's something which, because it has to be quarter wave. Okay. The other one is that you want to achieve phase difference of pi by 2. Okay. So if you put those two things here, you will find that R minimum, the minimum amount of reflection, is given by N1 square minus N0 times N2 divided by N1 square plus N0 N2 times the whole square. Okay. Now we want that R minimum to be 0. So if you put that 0, that means N1 square equals to N0 N2. That means N1, the index of the film, it must be equal to square root of the index of the incident medium times the index of the substrate. So in our case, N0, if it is air, it will be 1, and N2 will be the index of the silicon. So if index of silicon is 4 and air is 1, that means N1 is about 2. So what it means is, in order to get anti-reflection condition, the film material should have index of about 2.0. Okay. Now we will look at what material has that index. What about the thickness? Well, now we know the index has to be 2, and if you know the wavelength, we can calculate what the thickness of it. So everyone in the class should be able to design an anti-reflection layer, finding its thickness, finding its index for a given substrate, for a given wavelength. Okay. Any question? Okay. Now the refractive index of silicon as a function of the wavelength.
So the wavelength of the light that is being absorbed by the cell is not constant, right? Because we have a white light which has different wavelengths. So in that case, how do we design our anti-reflection coating?
Okay, great question. Let me repeat in somebody who didn't, very good question. Well, sunlight has a wavelength from UV to infrared. So, according to this equation, you will need different thicknesses to have anti-reflection for different wavelengths. So, how do we overcome that? Okay. Let me answer that question. Just give me a couple of minutes. So, this is how the refractive index changes as a function of the wavelength. Okay. So now we said we need a material with a refractive index of 2.0. So here are the list of the commonly used optical material which are transparent. Okay. So you don't have a lot of choices. You have very limited number of material which are suitable for optical applications. So here is the list. If you want a very low refractive index material, magnesium fluoride is a good choice. Okay. If you want index about 1.4 and 1.5, then silicon dioxide is a good choice. If you want 1.8 or 1.9, aluminum oxide is another option. If you want about 2 or 1.9, you have silicon nitride and TiO2. You want higher than tantalum oxide. But all these oxides and fluorides and nitrides are transparent in the optical part of the spectrum. So they act as anti-reflection without losing light through the absorption. You cannot use absorbing film, because then you will be losing that light. So the film has to be transparent. Okay. So these are the things. Now let's look at the plot. We calculate the reflection as a function of the wavelength. First we do for bare silicon, no inter-reflection. So the curve, dotted curve on the top, that shows you how the reflection of silicon will change as a function of the wavelength. And you can see from this graph, if you are about, green wavelength, it's about 35-38%, and then it even goes higher to 60% in the short wavelength UV. So that is what you're trying to reduce, that reflection. Now we put a film above index of 2.0, which is, let's say, 2.3 close. That's close. Okay. If you put a TiO2 film on top of silicon and you put 70 nanometer, that 70 nanometer comes from this number, from this equation. Okay. So you put the index and wavelength, you get 70 nanometer. Notice what you have, a solid line. You have a reflection almost zero, only at one wavelength where you satisfy the anti-reflection condition. That's what was the question was. Okay. When you have multiple wavelengths, you are fixing the thickness and index. You cannot satisfy the condition for minimum reflection for broad wavelength. And that's why you have this issue. You have low reflection at, let's say, 0.6 micron, because that's what we designed the thickness, 70 nanometer. Then the reflection increases, and it gives you how fast it increases based on the index of the silicon also. So that is not really quite a true anti-reflection for solar cell. Okay. So what people do to overcome that problem, they try to add a couple of different layers, okay, designed with multiple layers, because our formula and discussion was limited to single layer. But then you can now have a software which allows you to calculate for multiple layers. So if you put a 70 nanometer of TiO2 and then put 110 nanometer of magnesium fluoride, then you get a curve like a dash curve. And notice that in the visible part of the spectrum, reflection is around 5-6% over a broad spectrum. So this is how you overcome that problem, having a broad wavelength and trying to make an anti-reflection layer. Is that answer your question? Okay. Anyone has any question? Okay, so we learn how to calculate reflection. We learn how to calculate the index of the anti-reflection layer. We learn about how to calculate thickness of anti-reflection layer. And we learn how to minimize reflection over broad wavelength. Okay. And some other graphs. The 2 points to note from this graph. The reflection which I mentioned to you, 35-40% for silicon, that is between air and silicon. But if you put a another polymer layer on top of silicon or a glass, then that reflection is not 35%, because the index change from silicon to glass is smaller difference than change from silicon to the air. So the dash curve top here, that is the reflection of silicon when you put a glass on top of it. And the top solid curve is for bare silicon on air. Okay. And then you can also put different indices of anti-reflection layer and then watch how sensitive is it to changes in index. Okay. So this gives you the changes in index and how the reflection changes. Okay. Okay, so that's about what I want to talk about, the anti-reflection. Anybody has any comments or any discussion points? What we discussed for silicon, same methodology applies to other materials. So don't think whatever I talk to you is limited to only silicon. Those formulas are valid, much broader. So if you're trying to reduce the reflection of a gallium arsenide or your glass window, same formulas apply. Okay, now I'm going to introduce you to another method of reducing the reflection. Okay. Instead of having a nice, smooth, polished, shining silicon surface, we can make it like this kind of a rough and triangular texture on the surface. And then look at what happens to the light when it's incident on this textured surface versus a plain smooth surface. So let's say light is coming at 35 degrees. The cone angle of the texture is 70.5 degrees, and I will explain you where that number comes from. Okay. So now the light comes in, some of it will be reflected, similar to like glass, some will be reflected. But now you have another textured cone that will also allow light to be refracted again. Okay. And then you have a little bit reflection. So what you have done, you effectively increase the path length of the light traveling in the medium. Okay. It's not like straight going this thickness, but it is going at an angle, and then you have another part of it going again. So that increase in the path length for the light beam translates into enhanced absorption or reduced reflection. Okay. So by texturing the surface, you can trap light. So here is a question. If I take a silicon wafer and I texture it and I look at my eye, okay, what do you think the color will look like? Okay. So what should I be saying? Okay. Yeah, because you are not reflecting it. So you are absorbing, so no light coming to your eye, it will be close to gray or black. And that's how people do actually, is if you can texture that silicon, okay, and you look at that, no anti-reflection, just a texture, okay, it looks black. Okay. And black means you have really reduced the reflection now. These angles, 70.5 degree, all these comes because in solar cell, the silicon wafer they use is monocrystalline. So monocrystalline will have a crystallographic orientation, like it will have 100 orientation. Okay. So 100 crystallographic orientation forms normal to the silicon surface. So now you take that 100 surface, and people have found a chemical agent where you dip this silicon 100 oriented in a special chemical. They etch one orientation, crystallographic orientation, differently than the other. So 100 could be etched different rate than 111. Okay. And 111 plane that's what 70.5 degree comes from. Okay. So what happened is when you etch it, you lost that 100, but you created that 111 plane. Okay. So that 70.5 degree comes, or 35 degree, that comes from that crystallographic orientation. So by doing this kind of things, you can reduce reflection from, let's say, 35% to about 10%. The reason is because you can see that it's still, some light is still reflected, so it's not going to zero. Okay. So how do you make it even, there is a question now. So how do you really now make it almost zero?
You could do anti-reflective coatings and the textured surface.
I'm sorry, say louder?
You could do the anti-reflective coatings and the textured surface.
Okay. Okay. George is correct. Is why not we combine what we learn, put an anti-reflection coating on this textured surface. Okay. And that will really reduce reflection to about 3%. So people now have really minimized the reflection loss for silicon wafer for solar cell from 35 to 40% to about 3%. And that's why when you look at solar panels, some of them look like pretty gray or dark, black, essentially. Okay. Because they have this anti-reflection and some have this texture, so light reflection is really minimized, and that's why they look black color on the rooftop. Okay. So, if you take a silicon wafer, if you put in an acid box, it will not give you any microtexture, because what the acid does, it etches 111 plane and 100 plane same way. So it does not give any crystallographic orientation dependence etching. We call those isotropic etching. It is isotropic, it doesn't matter what orientation. But if you take sodium hydroxide mixed with alcohol and deionized water, that sodium hydroxide etches 111 plane differently than 100 plane. So what you are seeing in a scanning electron microscope image of a nice smooth silicon surface which has been etched into sodium hydroxide, IPA, and deionized water solution. Okay. Notice in this thing, the scale bar is 1 micron. So the average spacing between these cones is order of a few micron type. So that's to give you the kind of the scale of the roughness which you can achieve by anisotropic etching. Okay. So this has become mostly a standard process now for solar industry for reducing reflection is do chemical etching. Of course, if somebody can come up with almost less than 1% reflection, that even will be better. The problem is it has to come at similar cost to what we can do by the chemical. If you can add too much cost and reduce reflection, that doesn't make it as appealing. Okay. So this is how people use. Now, I have shown you for this application for solar cell. Some of you may go in your research and same method could be used for photodetector applications or for other applications where you want to create a black surface. Okay. Highly low reflecting surface, if you can etch it and put anti-reflection layer, you can really reduce the reflection. Okay. Any question? So this watch is not right. Potent. So to get this texture, we use chemical etching by KOH or sodium hydroxide. And 1G0 orientation forms pyramid structure generate low reflectance, and anisotropic etch rates for different crystallographic plane 100 versus 111 gives you that. Okay. So I'm just summarizing. Path length of light absorption increased due to the roughness. Now this is interesting. When you go to thinner wafers, instead of 200 micron, you want to go to thinner 100 micron to save material cost. There the traffic reflection loss minimization become even more critical because you have to absorb that light into 100 micron. Okay. So trapping that light into 100 micron is a little more harder than doing in 200 micron. So this texture and anti-reflection used for thinner wafer is even more important, and even becomes more important if you use thin film solar cells. Okay. The interesting thing, you have heard some presentations from various students, like today Matt gave on the perovskite solar cell. Couple of other students have talked about perovskite. Is this problem same severe in perovskite as silicon? The reflection loss is very high for silicon, about 35 or 40%. So it is a severe problem, and we had to find a solution. In the case of the perovskite organic solar cell, do you think it is as severe? We have to do the same? If not, why not? It's a reflection loss. Okay, the point I want to make it that 35–40% reflection loss comes because silicon has an index about 4. Does your glass window have 40% reflection loss? No, it's only 4%. The reason it has 4% because glass has a lower index, 1.5 versus 4.0. So perovskite don't have 4.0 index. They may have around 2, and so it's not as high reflection as you would expect in silicon or gallium arsenide. Okay. Now, people use monocrystalline in a single crystal wafer, but then a lot of people use multicrystalline silicon also. Now, the method we talked about is applicable if you have single crystal, because you have 1, 0, 0 orientation and you create 1, 1, 1 plane. But if you have multicrystalline silicon, how do you deal with it? Well, you deal with it, this method will not be applicable. Okay. So then people have developed some acid-based methods to use for multicrystalline wafers. People have used other methods like chemical assisted etching with SF6 or even a pulse laser ablation process for microtexturing of surfaces. So if you can, here is a plot of a reflectance versus the angle of incidence. Nobody asked that, because sunlight, is not coming normal all the time, right? So the reflection changes with the angle. Larger the angle, the reflection increases. So we need to also worry about that part of it. Okay. Here is a plot or graph, reflectance percentage as a function of the angle of incidence, and what is for laser textured surface. And you can notice that laser texture, the textured part, is really have very low reflectance, like 0.5% over 5 degree to almost 60 degree angle. So that's another nice part about these textured surfaces, okay, that they are also not as sensitive to the angle. And again, for sunlight you don't have to, it's unpolarized, but if you have a laser light, then you have to worry about polarization effect too on the reflection. Here is an SEM. Look at the scale here. This is 200 nanometer, not 2 micron in the other SEM. This is a 200 nanometer, and look at this has been a porous structure, nanoporous structure has been created on silicon. And this also gives you nice black surface. This does not give you black surface with the principle we discussed, multiple reflection. Why is that? Because in this case, the periodicity in the texture is much less than the wavelength of the light. Okay. So you cannot apply that ray optic type picture, reflecting and the ray going there and reflecting again. That's not applicable when you are in a sub-wavelength regime. So these are called graded index structures. Means you really decrease the index from 4 from silicon and slowly decrease it to 1, So that graded, and that graded index gives you low reflection also. So that's a different principle. Now we look at the losses due to non-absorbed light, long wavelength, okay. You have about 10% of the light which is lost for 200 micron thick solar cells, long wavelength. I'm not talking about beyond the band gap. This is up to the band gap. Okay, beyond the band gap you have even more loss. So then you have to put some kind of a reflecting layer on the back surface like metal and to capture that light. Okay. Okay, let me look at few more graphs. This is we talked about the reflection loss. This talks about the shadowing loss. Okay, by putting a metal contact on the top. How does the shadowing loss? So the vertical axis is the total loss in percentage as a function of the number of fingers we should use for the top. For different widths of the fingers, 30 micron wide, 50 micron, and 100 micron. So what it allows you to know that you need to put at least about 10 to 20 fingers. Okay. If you put too small, the loss becomes high because then you have too much recombination also. Okay. So you want to put 30 micron at least, with 10 or 20 fingers to be able to get low loss. If you put too many fingers, then the loss increases also. So that's the loss due to shadowing. Okay. Now let's look at what we have learned about the various losses. Okay. We learned about the electronic loss, we learned about the optical loss. So now we can look at this complete picture. We have a sunlight which is 100 milliwatt per centimeter square. That's the power per unit area the sunlight is incident on the Earth's surface. So that number is fixed. Out of 100 milliwatt per centimeter square, for silicon, 21 milliwatt is lost due to because it just transmits through the solar cell. Its wavelength more than band gap. Okay. That wavelength does not get absorbed, so that gets transmitted. So right there we lost out of 100 a 21 milliwatt power. Okay. Then 32 milliwatt is lost because the light has blue wavelength, green and infrared, and the blue photon has more energy than the band gap of the silicon, and that excess energy is lost as thermal energy. So right there, from out of 100 milliwatt incident from the sunlight, you lost 32 from the thermal loss, heat loss, and 21% is from the transmission loss. Okay. So now you left is 47 milliwatt. That's all you have left. Okay. If you have 47 milliwatt, in ideal case, that should produce about 44 milliamp per centimeter square of the current density from silicon. Okay. So 47 milliwatt of light which is available for you for power conversion, that will produce 44 milliamp per centimeter square. But out of 44, you do have some reflection loss, 3% or whatever in our transmission loss. So you do have some loss. So that current drops from 44 to 41 milliamp per centimeter square. Okay. On the voltage side, the PN junction which you form, that can only give you, because of this recombination, it only can give you VOC of about 0.7 volt, okay, rather than 1.1 volt. Also, due to the series resistance, the fill factor can be about 0.8. Okay. So now, if you look at it, okay, best you can do about 21 milliamp per centimeter square current density, fill factor about 0.8, VOC about 0.7 volt. If you multiply this term and divide by the incident power, you will find you end up more like a 23% efficiency. Okay. So that's why, people now is getting about 20% efficiency, because ideally if you have 44 milliamp and 1.1 volt, you can get 32%. That's a theoretical. But practically you can get about 23%. And that's what people are, about 20-21%. Okay. If you can minimize optical loss to zero, make recombination loss to zero, you can increase that a little bit. Okay. So this summarizes the limitations which we are facing in terms of making high efficiency solar cells. Any question? Okay, I'm going to stop here and let's summarize what we have learned. Okay. Okay. So who likes to give me first what we have learned?